So in this case, we can see we've got a collision going on, and we're even told that it's about energy and momentum. So we have a train of train A going to the right, and so we'll specify right is positive and left is negative. Horizontally, 6 meters per second. Another train that is initially at rest, so V0 equals 0, shown in the diagram below. All right, so we've got a graph, so let's do some Oy-Zerga on this. Oy-Zerga. Now there are two curves on here. We have our blue car and we have our yellow car. So our yellow car is carriage B, and if we trace that out, it follows this. It behaves that way. And blue starts at 6, comes down like so. So we see those two there. And since there are two different curves on here, we might want to consider Oy-Zerga for both of those. So we've got the A and the B. So the origin, if we specify the origin is right there. So we're actually looking at a quadrant 1 and quadrant 4 situation. Y-axis is velocity in normal units, time, or the x-axis is time. And for the A car, we do have a y-intercept, and the y-intercept is 6.0, and that's the V0. And there is an x-intercept. And that x-intercept looks like at about 5.7 seconds. So the y was 6, and that's the V0, and our x is 5.7 seconds. It becomes 0. We can read velocity time. The slope is delta v over delta t, which is the acceleration, and the area is v times delta t, which is the displacement. And so for the B, the origin, y-axis, x-axis would be the same. But now if we look at the intercepts here, the y-intercept is V0 is 0 in the case of the yellow. And there is no x-intercept. And we have the same quantities for RGA. So we've made sense of this, and I'll trace out the horizontal axis here so we don't lose sight of that. And so now we go on to the next question, and it says, use the graph, and this is important, the total momentum of the system is conserved in the collision. Well, so we are being asked, is the momentum conserved? Does P0, does it equal the momentum afterward? Well, beforehand, we have the momentum of A, and afterward, we have the momentum of A prime and the momentum of B. So we have MA, VA, and MA, VA prime plus MB, VB. The mass of A is 500, and the velocity is 6. Afterward, we have our 500 mass, and we see that it is -1. Afterward, our cart with a mass of 700 has a velocity of 5. So we have 3,000 equals -500 plus 3,500, and we get 3,000 equal to 3,000. So we have confirmed, yes, indeed it is. So the question was, the total momentum is conserved, and we could say that the total P is conserved because P0 is 3,000 kilogram meters per second, and afterward, P is also 3,000 kilogram meters per second. So that is the first part. Second part, that the collision is elastic. That the collision is elastic. Well, for the collision to be elastic, we need for the kinetic energy to be conserved. So I'm just going to erase my paragraph here and do this right next to it so it's easy for us to refer to the graph. So now we're asking, does the kinetic energy initial equal the final kinetic energy? Well, we have the kinetic energy of A beforehand, the kinetic energy of A prime afterward, and the kinetic energy of B. So we have 1/2 mv squared, MAVA, we have 1/2 MA VA prime squared plus 1/2 MB VB squared. Now we notice all three terms have, every term has 1/2 in it, so we can take those out because we're just trying to determine whether they're equal to each other. So our mass of A is 500, and our velocity is 5, and afterward, or excuse me, is 6. (500 times 6 squared). And afterward, we have the same 500, but the velocity is now -1 squared. And mass of B is 700, and its velocity is 5 squared. So you notice we have 500 times 6 squared, so that's 500 times 36. And this is -500, and this is plus 700 times 25. So this is a 500, and there's 36 500s over here, so subtracting it gives us 35 500s will be equal to 700 times 25. So I'm going to be kind of fancy here, show you a nice little trick. We have 5 times 100 times 5 times 7. And over on this side, we have 7 times 100 times 5 times 5. And it allows us to show that they are, in fact, equal to each other. So we have just shown that the kinetic, it is elastic because the kinetic energy is conserved. And that's what we would say, that the kinetic energy before is equal to the kinetic energy afterward. Calculate the magnitude of the average force experienced by the train carriage B. So the average force, well, we have a conservation momentum situation, so this might be a perfect time for our impulse. F net delta T equals delta P equals M delta V. We are looking for the force. We know the mass of B, and we know the change in velocity of B. And what we are looking for then is the change in time. So the F net will be equal to M delta V over delta T. Oh, the definition of the rate of change of momentum, delta P over delta T, is M delta V over delta T. So we have the mass of carriage B, which is 700, and it goes from 0 to 5, 5 minus 0. And the time over which that happens, well, that time, it starts to accelerate at time 4, and carriage B ceases at 6. So we have a time interval of 2 seconds. Over 2 seconds, so that's 350 times 5, which is 1,750 newtons. Now the question is how many significant digits? We certainly don't have 4. You know, the best we could say is 2.0, so we could report 2 significant digits from the time. So that's 1.8 times 10 to the 3rd newtons would be the net force. The average net force experienced by train carriage B. Train carriage B, we could check the sign on that as well, but train carriage B ended up having a positive velocity, so the force on it was positive. So the average force it experienced is positive. And so we can leave it as that. And that is how we do question A20.